Okay, good morning everyone. I hope you all have started writing all your notes in your classworks, and even in the first chapter, have you started doing your exercise questions in the homework notebook? I would suggest you all to finish it off, because you never know, the when the school reopens, and then we won't have time to cover and write so much. So as such also, you have boards, so do not delay, do not take it lightly that you have holidays. You do have holidays, but then invest in your studies properly. Okay, you're getting ample time right now. So and next class onwards, please join on time. We will wait for 5 minutes, at the most 5 minutes. Okay, beyond that we cannot really afford to waste so much of time, because you have the other other subjects classes also. So let's start today. In the last class we were discussing what is atmospheric refraction. We just touched upon two examples, but today we will be going deep into atmospheric refraction. Okay, so now understand what is atmospheric. Let me just first give you a brief about what is atmospheric refraction. Now see, we have atmosphere around the surface of the earth, and this atmosphere, suppose if this is the earth here, this earth has got various levels of atmosphere. Okay, and at all these levels you have here, let's say this is your first layer, this is your second layer, and this is your third layer. So the density in these layers will be different. How will it be different? Here in the first layer, this environment will be much denser as compared to the environment above here, right? The first layer of the atmosphere will be much denser. Why will it be much denser? Because you have many particles, and the kind of atmosphere that you have is a heterogeneous atmosphere, which consists of many types of particles, right? You have dust particles, you have water molecules, you have smoke, so this is a heterogeneous atmosphere here. So the density is going to be very high, but the density here in the second layer of the atmosphere is going to be slightly lesser than, or slightly rarer than, the first layer of the atmosphere. As you go high, what would happen is the number of molecules would start to reduce. Okay, so as you go in the third layer of the atmosphere, then the number of the molecules in the atmosphere will start to reduce. So this layer, as you go higher and higher, again the density will keep reducing, right? So the topmost layer of the atmosphere will be the most rarer atmosphere. Okay, and the last atmosphere, that is just the atmosphere which is right above the surface of the earth, would be the most denser. Okay, so you have to understand various levels of atmosphere, correct? So now understand that if the light ray travels from rarer to denser medium, just remember, what did we study? Whenever light ray travels from rarer to denser medium, what will happen? The light is going to bend towards a normal. So here also, suppose there is a light which is coming like this. So at this point the light is going to come straight, but as it enters, now this is a rarer medium, as it enters medium 3, okay, the layer 3, as compared to this layer 4 is a slightly denser medium. If you compare these two layers, if you compare layer 4 and the atmospheric layer number 3, which is denser, number 3 is slightly denser as compared to number 4. So it is going to bend towards a normal. Okay, if we draw a normal like this here, if we draw a normal like this. Now again, now the light is entering from the third layer to the second layer. So out of the second and the third atmospheric layers, which one of them are comparatively more denser? The second layer is more denser, right? So again, now how is the light entering? The light is entering from rarer to denser medium. It is going to bend further. Then Now where is the light coming from? The light is coming from the second layer. It is entering into the first layer. So here, which one is more denser? Layer 1 is much more denser as compared to layer 2. So again it is going to bend. So what is happening? Continuously the light is getting bent towards the normal, and it is coming from here at the surface of the earth. So in very plain and simple sentences, understand that whenever light travels from the higher levels of the atmosphere to the surface of the earth, it is continuously getting bent. There is this bending takes place. This bending takes place precisely because of different refractive index. Why is the refractive index of every layer different? Because the density is different. At some layers there are more number of particles inside the atmosphere. At some other layer there are less numbers. So few layers are denser, some layers are rarer, right? Because the density is different, that's why we have different refractive index. And because refractive index is different, I told you the light will either bend towards the normal or the light is going to go away from the normal, right? So this type of bending is called as atmospheric bending or atmospheric refraction. Okay, is this thing very clear to you? The way the light bends is known as, this phenomena is called as atmospheric refraction or atmospheric bending. Okay, so this application, we will study the application of this atmospheric bending or atmospheric refraction in the next slides to come. Okay, so shall we move ahead? Next one is, now look at this picture which is right onto the right here. The boy is looking at a star, and what he sees is the star's actual position is this. This is the actual star here. This is the actual star here. Okay, this is the actual position of the star. But when he sees it, he actually sees it slightly high. This is the apparent position of the star. So the actual position of the star is position number 1, at position number 1. But he sees it here at position number 2. So first point, this is known as the real position. This one is known as the real position of the star because star is at this position. But when you view it from the surface of the earth, this position number 2 is your apparent position. This is your apparent position. What do you mean by apparent? Apparent means some false position. Okay, actually the star is not there. The star is slightly below this position. But how do you see a star? You see the position of the star slightly higher than the actual position of the star, right? So even if you're viewing the star from earth, or you're viewing any body from the earth which is at a much greater distance from the surface of the earth, you would find that you will not be viewing the true position of the body, but you would be viewing the apparent position of the body. Okay, now why is there a difference between true position and apparent position? Why do you have two positions? Okay, actually there is only one position, which is true position, but what you see is not the true position, but it is the apparent position. Okay, or you can say false position. Don't use this word false. This is just to explain to you that it's a kind of a false position. Okay, now why do you see that? Let's understand again. Let's say you are here again viewing a star, okay, which is at very great distance from the surface of the earth. So suppose if this is the star that you're actually viewing. Now look at this. All this while when the light from this star is actually traveling to the observer who is standing on the surface of the earth, what is happening? Actually the star is here. The star is here at position number 1. Let's say this is the position number 1. Actually the star is here. But what happens? Suppose the light starts coming from the star. So the light will initially travel straight like this to the first layer of the atmosphere. So this that I've shown is starts here. First layer of the atmosphere is starts. Okay. Now the light will initially travel straight like this without any bending, because the above a certain level there is actually no atmosphere. This light is going to actually travel straight like this. It won't get scattered. But after it actually encounters the first boundary, the first layer of the atmosphere. What happens is, now suppose this is my, let's say this is my first layer of the atmosphere, not means the layer which is just above the final layer of the atmosphere, the top layer of the atmosphere, and this is my this okay, this is my second layer of the atmosphere, then the third layer of the atmosphere, and then the final layer which is just above the surface of the earth. So we have different layers, right? Now look at this. The light is first going to travel straight to this point as it encounters the first medium. Now tell me, out of 1 and 2, which one of the medium do you think is more denser as compared to each other? 1 is more denser or 2 is more denser? Yes, it is the second layer, the second, where I have written 2, number 2 is much more denser as compared to the first one. If you compare 2 and 4, obviously 4 is more denser. If you compare 2 and 3, obviously 3 is more denser. But if you compare 1 and 2, the second layer which I have marked is more denser than as compared to the first layer. So what is going to happen? The light is going to bend like this. Now compare 2 and 3 now. As it enters the third layer, again 3 is more denser, so it is going to further bend. Okay? Yes. As from 3 it is coming even closer to the earth's surface, it is further going to bend like this. So the last ray, the last path of the light that we see is actually this. The last one is actually this. Okay, so what do we feel? We will feel that the light must be entering from somewhere here, okay, something like this. So this position becomes our apparent position. Okay, actually the position is only 1. At position 1 only the star is placed, but we think that it appears to us that this is where the star is at position number 2. So position number 1 becomes the true position of the star, where the star actually is, and the position number 1 becomes the actual position of the star, where the star is physically placed, but position number 2 becomes the apparent position of the star, okay, which is not the true position. So this is how the bending of any light which is coming from a higher levels of atmosphere will take place. Let's also understand one more if you have not understood it. Again, I'm repeating it once again. So let's say you have this a person is on the surface of the earth, is standing and he is trying to look at a star. So the position, this position here, position number 1, that becomes the position number 1 becomes the true position of the star, where the star actually is. But look at this. So from the true position of the star, the light is going to come like this. It is going to travel straight. As it encounters the first layer of the atmosphere, it will first analyze, okay, which layer is denser? Number 1 layer is denser or number 2 layer is denser? So he will understand that number 2 layer is more denser. Okay? Okay, or so we see the apparent star. Okay, Anamika, we see the apparent star here. Okay, so the light is going to bend like this. Fine. Then next, again it will encounter the next layer. So again it is going to analyze, is number 2 layer where I am currently in, is that is more denser, or the next layer where I am entering is more denser. So number 3 where it is entering is much more denser. Fine. Okay. Next, number 4. Okay, so the last layer is even much more denser. Fine. So this is how the bending will take place. Okay, what I'm going to do is, if my voice is not audible, just wait for 30 seconds. I'm going to disconnect and connect again. Fine. Okay, now am I audible? Now is the voice clear? Okay, fine. So now this slide is very, very important. This slide is very important. Why the apparent position of the star appears high. Okay. This slide you got to note down all the points why the apparent position of the star appears high. So now we have learned why does it appear high, but I've just given you all the points here so that you can just copy these points straight away and make your own notes. Okay. So understand the first point. Why is the apparent position high here? Because firstly, the refractive index of the medium is gradually changing. Is that all very clear to you? How is the refractive index changing? Yes, the refractive index is changing because see, if this is the eye and these are the various layers of the air, then the topmost layer here, the first layer is going to be rarer. The second one is going to be denser. The third one is going to be further denser, right? So refractive index of every layer is gradually changing, right? This is understood? Okay. See, most of the rays will get refracted. Saksham, most of the rays will get refracted, you know, because there is no other medium here. The light cannot go anywhere. Even if few are reflected, we won't know about it. We don't have any data about it. Okay. Now, next is the atmospheric refraction occurs in all the layers of the atmosphere because all the layers of the atmosphere are different. They have different density, different refractive index. So refraction is going to occur at all the layers. Suppose for example, all these layers have the same density. There is no change in the density. Okay, so what would happen? There is no refraction which would have taken place. But now because each layer has got, you know, different density, different refractive index, refraction will take place. What is refraction? I told you refraction is only when light travels from one medium and enters in the second medium. It is refraction. So here the medium is changing every time. So that's why refraction, atmospheric refraction, you got to write atmospheric refraction will take place in, it will occur in all the layers. Okay. Next is the star light will bend towards the normal. Every time it is going to bend towards the normal. Why? Because the light is traveling from a rarer medium to a denser medium. Okay. That's why it will always bend towards a normal. Next is the apparent position of the star is slightly different from the actual position and it appears high. That's why the apparent position is different from the real, from the true position, because what we are seeing is only an apparent position. Okay, so these are the 4 points that you have to jot them down in your notebooks so that you can make good notes of the very, very important questions. Okay, fine. So next question which is linked with this question is why do stars twinkle? Okay, why do the, yeah, it is the same with sun also. Yeah, it is same with sun also. When we see sun, it is not the true position that we are seeing. It is the actual position of the sun. Okay. Okay. Next question is why do stars twinkle? Now, first point, why do stars twinkle? It is very, very logical. First is that the stars are very far away from the surface of the earth. You know, they are not as close as the planets are. So first point is that they are very far away. So I have marked here, this is a star here, and this is the earth from where we are actually observing the star. First thing is that they are quite far from the earth's surface. That is the first point. Next is they approximate to a point size source of the light. What do you mean by point size? Point size means only a point, only very small, because they are quite far, right? That's why they appear to us as if they're just point size. Okay. Since the physical condition of the Earth's atmosphere is not stationary, what do you mean by physical condition? Physical condition means sometimes the temperatures are different, sometimes see the density of every layer is different. You know, the particles are also continuously moving in the air. It is not like the particles are stationary, right? The particles are actually moving in the atmosphere. So that's why I say the physical condition of the Earth's atmosphere is not stationary. Okay, there like the temperature is different, the humidity is different, the particles are moving. So there is a lot of changes in the atmosphere which is happening. So The path of the light which is coming from the stars also varies. For example, suppose you light a fire. I gave you the other day, we were talking about lighting a fire. When you light a fire and when you look through that, through that atmosphere, suppose there's a fire and right at the opposite to you, your friend is sitting. So when you look through that, what do you see? You see your friend's image a little waving, right? So why is it so? Because the atmosphere which is right above where the fire is lit is actually not a stationary, right? It is continuously moving, it is continuously changing. So that's why you also see that waving effect, okay, or a little shaky image you will see. So the same applies here also, because when the light is traveling from the star to the surface of the earth, this environment is continuously changing. The physical conditions are not stationary, so the path of the light will also change. It will also appear to you as if it is shaking, it is twinkling. Okay, the second reason is that the apparent position of the star is also not stationary. Okay, the apparent position of the star is different from the true position of the star. Okay, that is the fourth point. The amount of the starlight entering the eye flickers. Sometimes the star would appear bright and sometimes the star would appear a little fainter. So suppose if the environment is stable, then it would appear a little much more brighter to you. Suppose if it is waving, if it is flickering, then the starlight would appear twinkling to you, little fainter to you. So that's why the stars end up twinkling. Okay, so this effect of sometimes the star getting brighter, sometimes the star getting little fainter is known as your twinkling effect. So these are the 4 points which you must write in order to reason why the stars twinkle. Okay. Another question which has been put up is, ma'am, as the light bent towards the normal, then this diagram is not possible. Yeah. See here in this case, what I have done is, in this case, this is actually, this diagram, don't draw it like this. What I've just tried to in this diagram I've just tried to show you as to how are the different layers. Otherwise the diagram has to be something like this, and then something like this. So probably this is the true position. Okay, this is the true position and this is the apparent position. So this way you can draw, or you can slightly tilt it further, like as I've drawn in the previous. Okay, fine. Yeah, the path of the light ray coming from the star varies continuously. The third point is this. Why will it vary continuously? Why will the path vary? Because the environment is not stable. Understand that the environment is not stable. It is continuously changing. Okay, the molecules are moving continuously, and this heterogeneous environment that is there, that is continuously changing. So something which changes continuously, if you look through such an environment, it would look as if it is flickering, or it is shaky, it is twinkling. So it would appear to you like that. Okay, fine. Does that answer your question? See, nothing twinkles. Saksham, nothing twinkles. It is only when we see the stars from such a large distance, then it appears that it is twinkling. Otherwise, it doesn't twinkle. Next, now this would answer you, why don't the planets twinkle? Now stars twinkle, we know that. Okay, at least they appear to twinkle. But why is that the planets do not twinkle? First point, as I told you in the previous case also, the first point would be that the planets are much closer to the surface of the earth as compared to the star, first of all. Okay, next is, now just this is the planet that I have shown here. This is the entire planet. Now if you consider the planet, suppose, have you seen those torches in which you have small LED bulbs? Suppose 50 LED bulbs are there in that torch. So what would happen when you light them? All 50 would actually get lighten up, right? So the light is coming from all 50 of those small little bulbs that are there in the tube light. So in this case also, if this is the planet, this is the planet, just imagine that whatever light is coming from the planet, that light is made up of small point size light sources. Okay, the entire planet can be considered as to be consisting of small point size sources of light. Small light point size sources of lights are there, and these sources of light are actually giving out the light. Okay, and these lights are going to travel to the earth, right? Now what will happen is, every single, understand this point very carefully, every single point source of the light, every single small dot, the blue dot that I have shown here, which is the source of the light, is going to flicker. Every small point size source in that planet is going to flicker, is going to twinkle. But when all these point size sources are flickering at the same time, they will nullify the effect. Nullify means they will cancel the effect. Together, when you see from this distance, it will not appear to you as if they are twinkling, right? That's why the planets do not twinkle. So look at the second point. Together, if we consider a planet to be a collection of large number of point size source of light, total variation in the amount of light entering our eye from all the individual point size sources will average out to be 0, thereby nullifying the twinkling effect, which means that every point size source, every blue dot that I have shown on the slide here, it is a small point size source. So every source will have some twinkling. Every source will have some kind of twinkling effect. But when all these point size sources come together, then it will nullify the effect. Okay, it will cancel out the effect. So you do not find planets twinkling. You only find the star twinkling. Suppose if the planets are at that great distance as same as stars, then even the planets also would appear twinkling to you. But now they are not as far as the stars are. So that is the main reason. Okay. So because the more the distance, the more the number of layers you have and the more twinkling effect you will have, right? The more atmospheric refraction you will have. Correct? So that is the reason why planets do not twinkle. Fine? Okay. Next what we have is, again, this is the third example of atmospheric refraction. The third example of atmospheric refraction, which is advanced sunrise and delayed sunset. Now the same applies here also. The same principle will apply here also. What is the principle? Now look at this. Look at this. Suppose during the sunrise, let's say the sun is here. Okay, when do you say the sunrise? We have sunrise now. Sun has already, come up. See, this line that you see here is called as horizon. Okay, this is called as horizon. So whenever the sun comes above horizon, then it means it is sunrise now. Okay, but till such time it is below. Okay, till such time it is below the horizon, then we say that still sunrise has not taken place. Okay, so now let's say this is the actual position of the sun, which means where is the sun now? The sun is below the horizon. Correct? Now, even if the sun is below the horizon, how is the light from that true position of the sun? So this is the true position of the sun is going to travel. The true position, from the true position, the light is going to travel straight like this. Why will it travel straight? Because from this true position till this first point, it is going to travel because there is no change in the density. There is no change in the refractive index of the environment. So it is going to travel straight only. There is no bending which will take place. Bending will start only when the layers of atmosphere, starts. Okay. So this whitish, that milky shaded area that you see here, this is where the layers will start. Layers of the atmosphere will start. Okay. So as soon as it reaches here, it will start to bend, further bend, and then reach the Earth's surface. Correct? So now, if we are standing here, how do we see the light coming? It appears to us that the light is coming from this direction only, which is the last direction of our path of the light. This is the last direction. This was the last direction. So it appears to us as if the light is coming from this direction only. So we see this apparent position here. So actual position is way below the horizon, but the apparent position, what we see, is above the horizon. So it appears to us that already the sunrise has taken place, okay, but still the sun is below the horizon, but we feel that the sunrise has already taken place, right? So now, what is the gap, what is the time gap between the true and the apparent position? Means the sun, when we see the true position here, but we feel that the apparent position is here. So the time gap between this is 2 minutes. For 2 minutes, we will feel that the sunrise has already, for 2 minutes we will feel that sunrise has already taken place. However, the sun is still below the horizon. So this will continue for approximately 2 minutes. Okay. The same thing is going to happen in the case of sunset also. Look at this. In the case of sunset, now the sun's true position will be the sun's true position will be here. Okay, just a second. This diagram. Yeah, okay. So the sun's true position is this. Okay, this is the real position. This is, I'm explaining you, at the time of the sunset. Fine. So now this is the real position. But now from this real position, how the light ray is going to travel? The light ray will travel straight like this, because till this point there is no change in the refractive index. Correct? And at this point, then when the first layer of the atmosphere starts, then the ray will start bending, and it will reach the observer here, right? So what will the observer feel? The observer will feel that probably the ray is coming from this last direction. This last direction means somewhere from here. So the observer will feel that the sun is still above the horizon. But where is the sun actually? The sun has gone below the horizon. Means sunset has already taken place, but we feel that sun is still above the horizon. Again, the time gap between is 2 minutes. When we feel that it is already there above the horizon, but actually in actual case the sun has gone down. So 2 minutes during the sunrise and 2 minutes during the sunset is the time that we feel the apparent position, right? So now look at this. This is again very important. Make a note of it. Look at what I have mentioned here. The sun is visible to us for about 2 minutes before the actual sunrise. Matlab, we feel that, which means we feel that the sunrise has already taken place, right? 2 minutes before. And even at the time of sunset, this is what appears to us, is that about 2 minutes after the actual sunset. And it is because of what? It is because of the atmospheric refraction. Correct? So 4 minutes is the delay. 2 minutes during the sunrise and 2 minutes during the sunset is the total delay. And this delay is because of atmospheric refraction. Okay? So these points have to be there when you start to explain why advanced sunrise and delayed sunset. You know, the reason. And why do we have apparent position and the true position? Okay? Why the planets do not twinkle and why the stars twinkle. So in all these questions, you have to have the term atmospheric refraction flashing in positively. Now the next example of atmospheric refraction and the next question that is important is, why is the color of the clear sky blue? Why do we see the sky blue in color? Okay, there is one more question which is put up. Ma'am, what about the meteoroids and asteroids present in the space which obstruct the light of the star? See, they are not, they are also moving. But the effect because of asteroid and meteors is very, very negligible. Means how many of us have actually seen an asteroid or a meteor? So we don't know. And it is very difficult to even capture the effect of these things because they rarely occur, and even if they occur, we are not there to observe them and to capture the effect, right? That's why. Okay, so next is, why is the color of the sky blue? Now understand that I have told you initially that the light which is coming from the sun, we know that it is white light, and this light consists of all the 7 colors. So when the 7 colors are together, what kind of light is this? It is white light, right? So the white light is coming. Now as the white light enters the atmosphere, Earth's atmosphere, so these black dots that you see here, these are actually the particles in the atmosphere, and I told you it is a heterogeneous mixture. Okay, in the atmosphere there are dust particles, there are air molecules, there is fog, water molecules. So as it enters the atmosphere, these particles are going to scatter the light. So suppose the light is coming, the first molecule is going to scatter the light like this. Okay, the second molecule is going to scatter the light like this. Further, wherever this light is going, again there are molecules, so they are again going to scatter like this. So these molecules are best for scattering the blue light, because blue light have got the lower wavelengths, lesser wavelength as compared to red and yellow light. Fine. So blue and the light which is lower than blue color, okay, which has got lower wavelength, lower than the blue color. So all those lower wavelengths will be scattered. Why will the lower wavelengths be scattered? Because we discussed it that if the wavelength is lower, then the scattering will be more. Didn't we study this in the Rayleigh's scattering? Rayleigh's scattering said that the intensity of light is inversely proportional to the 4th power of the wavelength. So the more the wavelength, the lower the scattering. The larger the wavelength, then the larger the wavelength, the lower the scattering. The more the wavelength, the lower the scattering, and the lesser the wavelength, the more the scattering. So they are inversely proportional, right? So here blue and the light which is below blue, these lights have got lower wavelengths, okay, lesser wavelengths. So if the wavelength is less, then the scattering will be more. So which is that light which will get scattered easily? It is the blue light which will get scattered easily. The violet will also get scattered, but when you mix blue and violet, the resultant will be a blue color. So that's why you see the sky as blue in color, because these particles are only able to scatter the blue light initially. Okay, so that is the reason why we see our sky blue. Okay, fine. So these are the points for why do we see the sky blue. Please note down these points. First is that the molecules of the air and the other fine particles in the atmosphere have size smaller than the wavelength of the visible light. Most of the particles here that we have, these particles are much smaller in size, and these particles are only able to scatter blue quickly. Okay, so that's why only the blue light initially gets scattered. These are more effective in scattering the light of shorter wavelengths at the blue end of the light of the blue end than the light of the longer wavelength, that is red. Means these are effective in scattering only the short wavelengths, not the large wavelength. They will be able to scatter only the short wavelength light. Okay. Now, next is the red light has a wavelength about 1.8 times greater than the blue light. This is just for your information. You may skip this point also. It is what I have told you is that here the red light has got maximum wavelength, more wavelength as compared to the other lights, which is 1.8 times greater than the blue light. Okay, so this is for only your information. When sunlight passes through the atmosphere, the fine particles of the air scatter the blue light more strongly than the red light. Okay, that's why the scattered light is all blue, and that is a scattered light which enters our eye. Okay, these are the points that I have given you so that you can straight away prepare your answers. Okay, otherwise you know what is the reason. I've already explained to you. Next question that we are getting is from Poonam. She's saying why don't we sun as it is blue in color? Okay, why don't we see sun as blue in color? Yes, we don't see sun blue as color. That this question will be answered in the next slides. Okay, so if this is okay, I'm going to, next is why the sun appears white as it is overhead. Yes, okay, these questions we are going to answer in the next slides to come. So first understand that why danger signals are red in color. Again, for the same reason, because red has got the largest wavelength. Red light has got the largest wavelength. That is why if it has large wavelength, red light will get scattered the least because of fog and because of smoke. Even if the environment is foggy, very smoky, even then we are able to see red light very, very clearly because it has got the maximum wavelength. Therefore, it can be seen from large distances also. So this is again an important question. Please make a good note of it. Okay, these small questions can pop up, so I'm just explaining. Your questions about why the sun appears white and all will be I have few more slides wherein you will understand that very carefully, but just hold for some time. Okay, next is why do astronauts see the sky black? What could be the reason? Now, after understanding the atmospheric refraction, you should be able to answer me this question. Why? Because there is no atmosphere only. There are no particles to scatter the light. The scattering won't take place. Okay. So first is there is no atmosphere. Hence there is no scattering. There has to be some particles strong enough to scatter the light, but there are no particles in the higher atmosphere, okay, in the space. That's why. So the sky will look absolutely dark. Okay, then I've mentioned a note here that the sky will also appear dark to all the passengers who are flying at very high altitudes. That happens very rarely because we hardly go up to that altitudes. Okay, at the max we go up to 37,000 feet or 38,000 feet or something like that. So till that point also you will see the environment is still not as rarer to not scatter the light. So some scattering will take place. Okay. So this is again a very important question. Can be asked why the astronauts see this. So I have actually prepared all the slides in such a way that all your questions are already prepared in the slide, so you can just jot down the answers and study them. Okay. Another question is, why do you see the sky orangish or reddish? Orange and red colors are generally mixed. And why do you see the sky orange or red during the evening or sometimes in the morning? So again, very important. The reason is that, see, when the sun is setting or when the sun is just rising, the sun is at one end here. And we are here. The sun is not over our head, but the sun is here at one end. So for the light to travel from that distance, so actually the sun is at a very far distance, greater distance. So for the light to travel from this distance, the light has to travel a very large distance to reach us. But when the sun is right at the top of our head here at the first position, so the sunlight will only travel straight. So when it travels straight like this, it is traveling lesser distance. But when the light is traveling from this distance during the evening and in the morning, generally the sunlights are traveling much more larger distance as compared to when the sun is in the first position. Okay, so this is the second position. This is during sunset and sunrise. So because they are traveling larger distance, what would happen? Initially here, as the sun light starts to travel, all the blue light will scatter. Okay, all the blue light will start scattering. Okay, now as it reaches somewhere here, slowly the next higher wavelength would start to scatter, because now all the blue is over. All the blue has been already scattered. So what is left when it reaches us is only yellowish and slight amount of reddish color. Slight amount of yellow and red light is left, which is unscattered, because the particles of the atmosphere are not able to scatter the red and yellow light. So what reaches us at such a large distance is only the yellow and the red light. Okay, that's why we see the sky reddish and yellowish mix, reddish orange is what we see the sky during the evenings. Okay, so that is the reason during sunset and sunrise. Okay, so this is again so there are 2 points which are to be noted here and which are to be kept in mind. First is, please make a good note, these 2 points has to be there, has to flash. First is greater distance. Okay, greater distance that the light has to travel. First is this, and second thing is atmospheric refraction. Okay, I'm sorry about my handwriting because I'm actually scribbling with my hand only. I do not have that digital pencil. So just make a good note of it. First point that has to be flashing in your answer is you have to mention that during the evenings and in the mornings the light is traveling from a much greater distance, because the sun is at much greater distance as compared to when the sun is there right on during the noon time, right at the top of your head. Okay, second is that when the light starts from such a great distance, first the blue light is scattered initially. So as it reaches us, what is the color, what are the wavelengths which are left? The color which we receive is yellow, orange and red color. That's why we see the sky yellowish orange or reddish orange in color. Correct? So these are the 2 points that has to be there in your answer. Okay, so again I have answered this question in 4 points. One is the color of the sun at sunrise and sunset is reddish orange. This is because during the sunset and sunrise the rays of the sun have to travel a long distance. While traveling such long distance, all the light rays get scattered initially. All the blue will get scattered initially. Red is the only color which gets scattered at the last. Okay, that because it has the longest wavelength. So with this, I think this is we should actually wind up for today. You have other classes also, but if there is any doubt till now, let me just take up all your doubts. You can write it in your chat box and let me know next 5 minutes. Yeah, see, another question, Devesh, because in the afternoon what happens is the sun is right at the top of our heads, right? So the sun has to travel a much lesser distance. So when it is traveling much lesser distance, what happens is basically except for blue light, there is no other light which is getting scattered. So what are the lights? As we see, only the blue is getting scattered. But how do we see sun? We will see sun as whitish or probably a little yellowish in color, right? Because the distance is